various architectures. There's one layer transformer, there's MLPs with several layers. But you will see an important geometric phenomenon that so you can embed them, you can make the input in different formats. You can do one-hot embedding and various other things. But in the trainable embedding layer, you're going to see a torus, right? So there will be some collection of frequencies at k, and it's going to give a number of frequencies that will be small compared to p, where your input A and B are going to be encoded into some torus, right? In some way, right? And this is a very nice geometric phenomenon. It's a very nice way of embedding a torus in the space. It's known as the Clifford torus, which happens to be a minimal surface in the three-dimensional. So you want to have something sitting inside S3, which sits inside R4. Same thing as 2. And you have this very nice manifold in your activation space. And so this motivates the question.
What does minimal surface mean?
I'll get to that in a second. So yes, I'm dropping this word to motivate why I want to introduce minimal surfaces. So minimal surfaces are the things that I study. So it's one of the old and rich tradition of searching under the light for your keys. And so the question is, what is a nice way to embed an n-dimensional manifold? In R. And we think of this n much larger, capital N much larger than little n. And because the space of all embeddings of manifolds is huge, if you don't have some kind of a notion of a simple or nice way, in the same way as we would want with functions, it is hopeless to find interpretable manifold features, right? So I think it's a very important question that I'd like to discuss and try to convince you that there is some particular choices of embeddings that are nicer than other embeddings. Okay, so let's start with a rigorous definition of what the manifold is. Right? So the manifold is typically defined as the space, the property that n-dimensional little people who live there and who don't travel too much and who don't have very precise instruments think that they live in Ark. And like the surface of the Earth, historically, and even still today, there are people who don't travel too much and think that we live in sub-Saharan. Okay, and for another example, we identify opposite sides of the square to get the torus. Yeah, and what's not an example is if you put three planes, three half planes, and you move them together on a line. You recognize this way, that way, but it's right here. You can see that you don't fit into the dimension. It's fundamental geometry. Okay, and so just kind of coming from a very general way of attacking this question, we have these classical theorems. We have the Yevgeny embedding theorem and the Nash embedding theorem that tell us into the same thing. So if you have any embedding, then you actually have an isometric embedding. So the same thing as proofs, but in fact, for example, you can isometrically embed a flat torus into R3. But not in a twice differentiable way, only once differentiable way. And also, if you actually want a smooth embedding, then there exists a C-infinity isometric embedding. All right, where this capital N is on your N squared. Okay, so the proofs of both of these theorems tell you that they're instructions. They tell you what to do. But they're not very nice instructions. So Whitney's theorem is mostly general position argument. That you can cover it by charts. This gives you an immersion into a very huge space. You can start projecting, and then by general position argument, if your ambient space is large enough, then you can do something like that and destroy self-intersections. You have two lines, you can perturb it a little bit, and they will not self-intersect. So these embeddings involve a lot of arbitrary choices. They're not very nice. Nash's first argument that is terrible.
We should actually make that 2n plus 1. Yeah? 2n plus 1. Otherwise, it's never.
I think 2n minus 1 you have counterexamples or compact. I'm talking about compact.
Isn't it an immersion for 2n and an embedding for 2n? Okay, I think, sorry, I think you're right.
And it's not just the gate, but I think certainly happens.
This argument works for 2n plus 1. Because like look at this exactly.
Which example?
The one you drew.
Oh, right. Well, no, these are conventional. Better. Sorry. Yeah, but the one-dimensional circles. Yeah, you can get rid of some. So the magic C1 guy is variable. You can't do the magic, right? So basically what Nash is telling me is that I can do this, I can have connected like that. And then I connect one end to another end without really doing anything, destroying the geometry of the surface of the paper. Right? And the way it's done is by introducing tiny waves and perturbations on a smaller and smaller scale. It's just pretty mind-blowing. And the other is a kind of Newton's method approach that's also not nice. Not very nice approach. So if we think about embeddings, we might as well think about a simpler thing. We might as well think about just functions. So what is a nice way to define a function? And so if you specify that the function has to pass through this point to that point, and you ask what is a good function that interpolates between these two, then you pick one, right? It's the simplest. And two nice properties about that. So why did we pick the line? Why do we think that it's the lowest complexity object? Well, first of all, it is the shortest path from one point to another. Another thing that you could say is that it actually minimizes the L2 norm of the derivative. So it minimizes complexity along all the things. And so these two simplicity demands you could push further if you have specified your function somewhere on the boundary of this. Then so here the boundary in the if we think of complexity as the amount of area, then we want to interpolate it in a way that minimizes area among all graphs with that boundary. Or if you want to minimize the square of the gradient, you can also minimize that option. And so this naturally leads us to two notions of minimal embeddings and harmonic maps. Okay, so that's sort of one inspiration from functions, and another inspiration, if you think about the simplest possible manifold, just S1, and you ask what is a nice collection of functions, you would think cosines and sines. Right? And on S1, cosines and sines with various frequencies are just eigenvalues of the Laplacian. Eigenfunctions. Not that. Eigenfunctions. So what I'd like to argue is that minimal embeddings, harmonic maps, and embeddings by eigenfunctions of the Laplacian are the examples of nice embeddings of manifolds in G-Arc. And we'll probably have time to a little bit talk about this one and that one, and this actually turned out to be kind of almost the same. Is this going okay so far? Do you want to switch directions and talk about something else?
That's like just a complete unrelated question.
Go ahead.
Does this have anything to do with the entropy physics?
With entropy of
Like there is like this whole discussion in holography about minimal surfaces, and
Mhm.
I was just wondering whether this is related to that, to what you said.
So it should be, yeah, it's like an area minimization.
Yeah.
Yeah, exactly. So if you have a soap film where you specify how wide you put in the soap where you put it out, then what you'll see there will be precisely minimal surface. So that's the solution. And if you have a soap bubble, then it's also a slightly different equation because you have a constraint that it has to bound a certain volume, but it's a similar equation.
Okay, cool.
Yeah, so these are very natural objects. Okay, so let me quickly talk a little bit about minimal surfaces. Let me erase something here. So let's do a quick change of problem. So we are looking at the map from n-dimensional manifold, and we want to think about it as a map into Rn. Let's actually think about it as a map into Sn. And if n is large, it's not such a big change because if you pick a random point in a 100-dimensional disk, that point will be at a radius greater than 0.99 from the center. So almost everything, almost all of the volume is near the boundary. 0.99 to 100 is a small number. Right, we can always move and scale our manifolds Rn. And the reason I want to make this change because in Euclidean space we actually don't have closed minimal surfaces, only infinite minimal surfaces, but in Sn we have. And so definition as a manifold, in this case the sphere, is minimum if it is a critical point of the volume of the n-dimensional function. What I mean by that is that for every variation circle into S2. That sends the circle to the equator. So the circle now becomes a subset of this two-dimensional manifold, S2. And if you consider various deformations of the circle, notice that the word minimal here is a little bit unfortunate and misleading. You can actually decrease length. If you just push it later to up or down, the length will go down. But it will go down in the second order way, right? So the first derivative, the derivative is zero. Yeah.
Show me the like magnitude point.
So
Magnitude point will be
map into quick will also be possible. That's a trivial. That's a trivial real sense. You map everything to a point. That's an example of a trivial real sense. So, however, notice that what you do have, so it's not minimal in the sense that the smallest area, smallest volume map, only in the sense of being a critical point. However, if you pick a small ball right here, a small disk, and you fix the endpoints, then between these endpoints, this portion of the geodesic is actually going to be length minimized. This completely short span. And because solving this equation leads to an elliptic function, this problem actually has this property that critical points are locally minimum. So that's it. It's kind of very nice property. It's an alternative way of defining what a minimal surface is that if you pick a small ball, then the portion of minimal surface is actually always area minimized.
With respect to nothing.
Sorry?
With respect to nothing.
Yeah, with a fixed value. Yeah. So that's one example. Another example is if you take a torus, so square, and you map x, y to e to the I x. So you get 2 pi. 2 pi I. Y. So that's contained in C2, but actually it's also contained in a 3 sphere inside C2. So this is a very nice embedding of the torus, and it preserves the geometry of the torus in the sense that it's a flat embedding. The magic used from the Yangian 4-dimensional space is going to be a flat metric, which is the product of two circles. You move along however you like, their kind of sizes are not changing. But it also lies in the 3-dimensional sphere, and it's not hard to see that it's actually going to be using symmetry. You can see that the new curvatures are always going to be the two principal curvatures. I can talk a little bit more about that. Excuse me. So this is another example of minimal surface. And in fact, it's a unique two-dimensional minimal torus in S3 axis rotation. Right. So that's one very nice way of mapping manifolds into Rn. That's in non-harmonic maps, which are minimizers of the L-normal derivative. And rather let me just skip to the last one. So another nice example of functions were eigenfunctions of Laplace operator. So Laplacian, let me
So just to go back, so theorem about this mapping, can you generalize it to situations where you have a topological manifold which is not smooth? Is there any such notion?
Yes, absolutely. That's a very rich theory, also standing called non-smooth solutions to minimatures, and something that was discovered by Jim Simons, before he became a billionaire, is that starting in dimension 8, you can have examples of non-smooth minimatures. So up to dimension 7, if you have some smooth boundary, then the minimal way of filling it will be smooth. In dimension 8, you can have a boundary, but the minimal way of filling it will be a cone. So that will have singularities, and in high dimensions will be even more singular, and the whole theory of manifolds and patterns has been developed to study this objects. A lot of people will be very happy with this something. This can be applied to safety. Right, and so what I want to say is that if you have a manifold M, then you can pick a chart, a map from Rn, that sends your axes, xi, to orthogonal geodesics, the curves of minimal length, and such charts are called normal coordinates or free coordinates. And so you can define in such chart the Laplacian function when you map it back to Rn, you can define it to be the same as the Laplacian in Rn. And that kind of gives you a local way of defining the Laplacian on the manifold. So this gives you a way to define Laplacian. And what's important is that these Laplacian will have the nice properties that you have some test function, then you have usual divergence. And so on any manifold, the Laplacian has a discrete sequence of eigenfunctions and certain eigenvalues. And it's easy to see from the divergence theorem that the smallest eigenvalue has to be greater or equal to 0. And corresponding to each eigenvalue, we have an eigenspace, which is the collection of all corresponding eigenfunctions. And so it's a function of that, such that Laplacian applied to that is designed can have the eigenspaces can have various dimensions depending on the manifold. And so for example, if you have a two-dimensional square torus, then your collection of eigenfunctions, eigenvalues, there's a theorem of Takahashi that these two are the same. So suppose we have an embedding of some n-dimensional manifold into some capital n-dimensional sphere. Then we can consider the geometry that's induced by this embedding. So define G to be pullback. Hopefully mining will be sort of the Euclidean metric comparing +1 to the sphere. Then F and N is the minimum submanifold. Minimum if and only if the projection functions ui, which is just composition of F with projection with the xi axis, are all eigenfunctions of Laplacian of F with this induced metric. It's a nice computation to do. And so this time we suggest that there's this very nice way of embedding manifolds into the n sphere that matches both of our intuitive simple guesses about what the nice manifolds. Both as embedded into the eigenfunctions of Laplacian and as a new concept. So with my postdoc, we tried to play around with various situations where you can see that, and we're still a little bit confused. It's a non-linear word, but I'm very happy to discuss this other situations. But I have very interesting results also relating minimal surfaces and harmonic maps of hyperbolic surfaces into spheres that relate to representations of fundamental rules of hyperbolic surfaces, hyperbolic groups. And that's also something that I have to discuss, but maybe I'm talking too much. With some other people. Ask or ask questions.
I can. What is the connection between this
And so,
and learning?
yes. So,
Specifically minimal surface.
right.
Particularly, yeah, right, in this question, yeah.
Right.
I think I know the story about unfolding. There's maybe something that cool that one can say about like mean good theory versus Gaussian learning. But oh yeah, so okay. What is the connection?
That's a great question. So I would so the manifold features that we're able to find so far, the way it goes is that you're solving some problem, say breaking a line on the text, right? And so you ask, what kind of manifold can I see? Well, it's probably going to be a circle, or you expect something that looks like a cube. So you know exactly what you're looking for, and then you find it. So it would be very nice to find more general ways of discovering manifolds and have a nice collection of things to look at. And so for smaller dimensional embeddings, which look maybe like minimal surfaces. So it's, something that we want to understand more carefully. So if we have a large collection of problems for which we can find nice embeddings of objects, I think that might be helpful to for manual features in complicated systems like LLMs.
You could think about probes for this sort of services. Like how would you probe for minimal surface within that?
Right, so locally it's pretty simple to check that the surface is minimal. So minimality means that the mean curvature is, you have a lot of data, a lot of points in it. And the minimality means that it looks a little bit like a saddle, but in a specific way. The two curvatures, the curvature in one direction and the curvature in the other direction, cancel each other out. So the sum of all curvatures is zero. In other words, the mean curvature is equal to zero. So you have a lot of points in it, then you can say that it's a minimal object. You can also try to consider various deformations of the surface using some approximations to mean curvature flow, which you use in imaging, and for which I think there are some reasonably fast ways of doing that. And that also, whether how quickly you can deform it with mean curvature flow will tell you whether it's mean.
I have a question. Somewhat crackpot, but I remember, I heard you correctly. I think there's some relationship between stuff like the word problem for finding percentage groups, like colors and stuff.
Yes.
So,
Right.
is it just a question of, or at least to me, if you train a network on something, find a percentage group, like, you assume that that's a solvable word problem or something like this.
Right.
Is that something that you need for all representations of factors, something? Minimal surface, like that.
Yes, there is a connection there between, there's a very recent work of a friend of mine, which finds a connection between some representations of hyperbolic groups and specific types of harmonic types, which is very fascinating. Because in some sense, what it says is that A equals a random collection of representations for sequence of groups. And the corresponding mass will have the full diameter is hyperbolic on the surface. I'm not sure how to see something like that in the observability setting, or how to discover a very complicated embedded hyperbolic surface inside SM.
Yeah, I guess this is very kind of counter to my future of interpretability. Because my sense is that like the things that one wants to interpret are exactly the ways in which you have non-local structures in your data. And like
Right.
I have like a kind of a story about this, right, which is that like there's these like two notions of geometry. There's like, well, in fact, there's like, so there's Riemannian geometry and there's algebraic geometry. In algebraic geometry, you care about sort of in some sense like polynomial structures. Like a quadratic surface is considered nicer than a quadratic surface, and you can kind of have an even stronger kind of the classical definition of classical algebraic geometry, where all of your quadratic surfaces are in fact embedded in some affine projective space, and you care about how they're projected, and you care about which polynomial is vanished. And so the story about modular addition is, so the story of barking is exactly the difference between this kind of local geometry and algebraic geometry, even when you're using a function like a sigmoid, but especially if you're using a quadratic function, in which case it's exactly the story, which is that what is it? What is modular addition? So you have some groups you might have. So you have like, or let's say P. Usually they use P because it's a prime. Sure. And you have about is kind of, it's like, it's more or less kind of has this local property, maybe with some linear regression, but the point is that like, as soon as you have feature learning, in feature learning sees Lagrange geometry, and feature learning sees this kind of like quadratically fitting, and so to quadratically fit, you only need constant times p, and this is what you need to generalize with the generalizing circuit. So once you have a feature learning, then actually like you have like you've not resolved any local structure. You don't still don't see the dimensionality of the flatness, but what you do see if you see this kind of Lagrange geometry, you see that there is a unique, so once you have constant times p, there's a unique quadratic surface that fits to your torus. And this gets learned even if your activation is not quadratic, just because like polynomials are nice. And so I guess like my story is that like if your like local structures matter when you're doing kind of Gaussian learning and like when you're maybe like starting to learn a new thing, but like the kind of really interesting structure that you see in machine learning and that you want to interpret is when you start getting these like long distance strong correlations due to kind of like, oh, these three, like we're seeing that these 5 points lie on this elliptic curve. Or sorry, lie on this ellipse. But how many do you need for an elliptic curve? You need more points. Like, yeah. But yeah, that's.
There's also a way of thinking about minimal surfaces in a more global way as critical points of the Boolean function in the space of all embeddings. That's how they're usually constructed.
Yeah, and like I guess a minimal surface is more likely as an embedding than it's also maybe kind of looks maybe. Is there a way in which the minimal surface looks lower degree? Is there some kind of link with? Of course, it's not going to be algebraic general, but is there some link with algebraic geometry where it's like
Right.
some kind of general?
Yeah. So for example, with this picture, if you're the eigenfunctions of Laplacian on S3 are spherical harmonics, right? So these are just homogeneous harmonic polynomials restricted to sort of S2 restricted to the sphere.
Yeah. So these are, by the way, exactly yes. So in this case, these are the functions that for two layers that like you can feature learn more are low degree.
Yeah, so in some setups you do get minimal surfaces with exactly represented by level sets of
Yeah, because like so like polynomials tend to get learned if you have like Gaussian data or like some kind of nice geometric data. Yeah, maybe if your data is a priori on this would be cool if you make some statement that if your data is on a manifold then the easy functions to represent are like are harmonic are eigenfunctions
Yeah, I think that was out of the top of my mind, and I'm curious to I think it's slightly maybe put more emphasis on these kind of control observations, but I'm curious to hear what other people think about it.
It's very general result that for hidden market models, you always get a fractal for belief state geometry.
You always look at
No, properties between the geometry and fractal. For generic.
I think generically you get a fractal, but not always. It's just.
You get a fractal with an infinite dimensional fractal.
Yeah, sometimes you just get finite.
I think for it to be infinite, you have to have so we're
That's very fine.
yeah.
And you don't get an infinite dimensional. The epsilon is infinite dimensional.
For hierarchical features, there are maybe very nice works presented at this one particular feature where we discussed this kind of rather physics paper, so if you do models to go if the data is hierarchical, yes, in this paper.
What was the reference?
Let me check, maybe I have it written down somewhere. Squatchy, 125. So it's a very nice, people already use, there's a Greenfield theory, you guys cited in your paper.
Yeah.
They use diffusion models to detect a certain phase transition which happens if your data is hierarchical.
Is this the main part?
Yes.
Yeah.
Has anyone applied that to space calculations? See which lesions come from hierarchy, which come or remain tested. Is this an efficient way of checking whether?
So this paper is the one that I think what I'm thinking of. The idea is so you have a hierarchical relation between all your features.
Right.
And so if you noise them at random, then that will propagate up, but you won't know like where what the true feature is. But at some point, because you have the rest of the hierarchy, you can correct that.
Yes.
And if you add more noise, at some point the error will propagate all the way up to the root.
Right.
At which point you're screwed.
Yeah.
You can't error correct anymore. And so in your diffusion, in the real diffusion example, it's like if you run the diffusion like part of the way and then you go back, it'll stay in the same class. Well, it'll look the same, and at some point it'll if it's a dog, it'll still be a dog, but at some point there's a critical phase transition where it returns to the image.
Right.
And they model that in this hierarchical
But from what I understood, you could also somehow use that to detect if you only see the bottom layer to detect whether or not it has this hierarchy structure. It comes from.
But isn't this relative
one starts with, hierarchical data, trains the model, like for example, your data, and tries to see how different interpretability tools like SVs work on that. Unlike a group of natural data, you know for sure that things hierarchical has a very specific structure. So does it tell you something about which ones work better or what are their shortcomings?
Yeah.
You kind of have a lead on that.
Um,
Some extent.
well, I think this is an area probably where we want to improve from state of the art. Typically, you just show it's non-hierarchical, your instruction is very good. If you also hierarchical, like Matryoshka city, then you get better reconstruction, and by how you get better interpretability of the features. But I don't think it's quite the same way in some specific metric of hierarchy. I don't know if you or Andrew know more than me on that. I think, yeah, well, speaking personally, I would like to do experiment with percolation data, as I haven't seen it on this little thing, but I think it's
But if, so Andrew's working on a sort of like more hierarchical SAE variant and there's been others, of course, but, yeah, one of, I think the idea as far as, like this research direction is exactly to evaluate tools. It's like, and say like, is it doing a good job of capturing this, the properties of data that we want?
Does anyone have more things to say or comments?
Yeah, but on the other one. I don't know much, but I know pattern matching. I heard manifolds, I know manifolds. And so Thomas Newman says a bilayer SE, and their method for finding manifolds, I think they've applied it in all these, is basically, in the decoder, you find directions that are pointing in the same direction. You're saying, oh, this model's saying the same thing in these rows. But then you look at the encoder and you see, okay, what are they reading? They're reading different directions. And, there could be a lot of them, and you do like the SVD composition on the actual dimension. But the important part is you project your data onto that. And then you get these nice looking manifolds. The problem was, I mean,
Project data on what?
on like
Space.
the encoder space on the voice.
Nice.
Which is nice because if you actually just do PCA, you're going to see variation in the data that might actually care for computation wise. Whereas projecting in the way, it's like, this is computation. So, he has examples on there showing like, oh, here's a nice like triangle 3D simplex shape. And like, oh, this corner is new for New York, and this one's like new is a newspaper. And this one's like words that precede new. And it's cool, and I looked at a few and they're all nice, and then I was like, man, I'm still limited by 3D. I just see it, right? And sometimes there's more than 3 singular values. So I'm just like, man, hopefully, maybe there's some tool here to analyze something more than 3D.
Like visualize this high dimension.
Yeah, there is structure that's higher than 3D models.
It's the projection from whatever the dimension of the critical surface is to something that we can interpret. So how do we think about it? What, so maybe you could say something about the, do you have a dimension or?
slower dimension actually looks like. And there's a famous conjecture of Kromov that if a manifold has positive scalar curvature, then it's secretly n minus 2 dimensional. And there are versions of that that if you have an n-dimensional manifold with positive scalar curvature, then it's well approximated by an n minus 2 dimensional manifold.
Like a sphere. Oh, a sphere
A
has
sphere has positive scalar curvature, but not just a sphere. Right, so for example, you can take a hyperbolic plane times S2. You can take the radius of the sphere very small, and then because the scale curvature is a trace of the trace, you can make sure that the space has positive scalar curvature. So from far away, it just looks like a hyperbolic plane. So that's the problem. And so there's a version of that embraces some authors, which is turned out to be in the end can be formulated. It just does something about metric spaces. And the claim is the following. So if you have X, so you can take this result for manifolds, but it's more general than that. If X is a metric space. And there are two sort of parameters here. So things are let me just take it out.
So there's no poster session, so you can just go.
But please feel free to leave and forcing everyone to listen to my theorems. So we take some parameter, and if you have the following property that so I'll explain what this is. It's called alpha content of manifolds. Let's read some constants. Depends only. Then
R here is the like the reach
Is this-
curvature? Or-
so R here is the radius of
Oh, the radius.
so it's a little bit, yeah, so the curvature and the curvature is a little bit confusing. Then X is well approximated by n-dimensional space. Actually, the space is not necessarily manifold, it's a solution complex, but if you one more dimension. And so what this alpha content is basically the sum of the infinite with the sum of Ri. Sum of all coverings of
What is HCM?
so this is n-dimensional alpha content. So you
This
cover
has a positive scalar curvature. Oh, no, so you just
so this kind of corresponds to having a positive scalar curvature. But what it says is that if you can take this, you have some large ball. If you can cover the intersection of that ball with your space by smaller balls in such a way that the sum of their radii of n is small, then your space is really can be approximated by something n-dimensional. Right. So for example, if you have a torus. And then it's very wiggly, you can add, so maybe it has a huge amount of area. However, any ball in here will be able to cover it, so it's with that n minus 1 dimension. covered in such a way that the sum of squares of the striking radii will be small, so that means that you can actually project. And it's a constructive proof to describe how we use tools and ideas for positive scale curvature. I'm just not sure how difficult it is to compute this quantity. That's why I never kind of thought about applying it to dimension reduction in this setting. So if you have a bunch of points, is it easy to find the infimum of the sum of radii to the power of n of the collection of false cover? Is the computation very expensive or not? That's something I
Already has been doing this kind of stuff.
yeah, I think I mentioned this yourself, yes.
Yeah, but yeah, I guess again, my message, right, that like I think like the big update, right, of like machine learning that's happened in the last 5 years, maybe also a lot longer, is that like these kind of vocal analysis that people did, yeah, they're so remember this picture that Zohar had in his talk, where you like vary parameters, and you would expect like there's like this expectation that people had when people study, you know, in the good old days, study the stuff that is going to look like a random Gaussian surface. So it's going to like have these like standard crazy like bulky structures, but that's not what you see, right? And the reason you don't see this is you have features, and features organize data in this kind of rigid way in space. So you have correlations between different things, and so like it's kind of like no longer like unless you're only doing like lazy learning, it's sort of like sorry, this still may be interesting, but I think like but it sounds like here right you're saying that there's actually kind of a connection between this maybe local statement and then it's kind of like more like you're looking at Hausberg relation, you're looking at like kind of small structures, and a statement that actually could be global, like some kind of rigid, right? Like you have some kind of like a minimal surface. Like it is like trying to produce rigidity, and like I think like the kind of like the message that I strongly believe is that like you want like learning is rigid, like it's rigid in space. You need to know how things like structures like algebraic structures exist embedded in space, and in a kind of like microscopic way, like sparsity you can't talk about locally. And yeah, like and I wonder if like are there some statements where you can kind of interpolate between this kind of local Hausberg dimension style analysis and something that's like maybe actually rigid, or like yeah, some structure but like you can I don't know measure some distances, like where like if you for example have like a surface with like some like small curvature, you know, that's big. That's the kind of statement that that you can make, and like yeah, so I don't know. Like I feel like the thing that I think would be most exciting learning is trying to understand the connections between these maybe more local structures and also this kind of global feature kind of like so like geometry that you care about for machine learning is not local. It's like you really care about this kind of question of sort of yeah like 2 points that are very far away might like know about each other because they share the same feature. And just like the point of feature learning is like the feature correlates points in an interesting way, not by being close. And like yeah, I don't know.
You're looking at things represented by a small number of bases of elements of bases, slows you to
Exactly. Or like it doesn't have to be like equivalence, but it has to be something with like rigidity across space. And so like having like controlling curvature or controlling like eigenvalues of the Laplacian, like if you actually control them right numerically, that this does give you these like large structures. Like I think a lot of like what Gromov thought about right was these kind of like big, like you can't fit a ball in a cylinder. And yeah, and like I don't know, like I guess yeah, the thing that I would be excited about would be like to try to find something of an interpolation between maybe a small structure that's local and a structure that has like this kind of big rigidity, like, and then see if you can kind of understand this in learning.
Maybe we could also talk about so you use the word nice a lot, right? The word nice has a nice property. So maybe this is like a question about what we miss from features from just having global structure, and like when we think about
here's the manifold, it's a really high curvature, or, really large negative curvature. Is that plausible?
If that's something that we'll see in the activation space.
Yeah. Like on projects, is that?
Right, so negative curvature makes things large, the volume grows fast, and it's very difficult to, for example, try to push a hyperbolic space. Just the two-dimensional hyperbolic space. There's no way around arbitrarily large dimension, arbitrarily large two-dimensional space. So for example, for hierarchical structure, that's relevant. Right? So I'm not really answering your question, but this is one thought that I had for hierarchical structure specifically. One thing measures whether it's delta hyperbolic. So there's this notion of delta hyperbolic, which says that if you have in your manifold, if you have 3 points, and you consider minimizing geodesics between them, then this triangle will actually be thin. So a small neighborhood of these two sides, delta neighborhood of these two sides, will contain the third side. That's how delta hyperbolic is defined. And so trees obviously have this property. Sides in the tree, they completely contain the third side. These 3 points. But that also makes these things very difficult to pack into RNA without large distortion. And you have theorems that say actually how much distortion you have to have, how large is the Liokumovich constant. I don't remember on top of my head what they are. But I think you have to maybe square the radius, right? So if you want to if you have a wall radius r in a hyperbolic space and you want to embed it into Rn, then without too much distortion, you have to embed it in the wall radius square, something like that. And so that gives you some intuition for to have very hierarchical data or something with very negative curvature. That means that in order to not distort it too much, there's only so much you can push into this small point.
I wanted to ask something, maybe it's not really anything, but so there is this like very large class of theory and model people have where exists a power like structure in neural networks, and most of them in this year explicitly end up putting power on their by hand, and by that I mean something like you start with a zero power structure in data, such that it's reflected in the laws or infinite structure or whatever. And I think there is a world where this is just a plausible and complete description of what exactly is a power law, but in some sense it feels unsatisfactory to me because you're like putting in the power law and then you're kind of massaging the whole thing where it appears differently. So what I want to ask is there some kind of case where like, okay, the data actually doesn't have an intrinsically power law structure, but because of some normative reasons about what kind of representation neural networks might form of the data, not that the data is intrinsically powerful, but because internally you're trying to form some kind of minimal surface, or some kind of interesting structure, because of some normative pressures of learning, you nonetheless end up with some power law structure without it being created. And what is the thoughts on that? Especially coming from like some notions of optimality in the neural representations.
That's a very nice question. That's not what what you're asking for, but for a generic manifold, if you start constructing, there's a general procedure for constructing minimal surfaces. called min-max theory. You look at more and more higher dimensional spaces of surfaces, and you minimize the maximum to find higher and higher critical points with larger and larger Morse index. And so in this case, it's an interesting fact that their volumes grow like bit of a month, not linearly, but sublinearly in this way.
The more or less the same parallel as the Russian I can
Exactly. Yeah. I actually proved kind of reliable these things.
Oh, nice. You mean just now, or in your paper?
In the paper, about 10 years ago.
So this is different from the statement that you said about the kind of duality between Russian and eigenvalues.
It's different. There's also connection between these. So that one was specifically for round sphere. This is a statement for any generic metric.
I see. So that one was for that makes more sense.
So it's a kind of very general theory and that there is in fact also a connection with that allows for plus n. But it's very non